All right. I assume everybody can hear me. If you cannot hear me, then let me know. I mean, just post on chat. I'm tracking chat. We don't have a link for attendance because Zoom keeps track of everybody who is in the uh, on the meeting, and so we know everybody who's here and for exactly how long you've been here. We're going to continue our series on convolutional neural networks. We're going to look at training neural networks. So here's a quick recap. We've seen, we're going to start with a quick recap. We're going to go through backpropagation through a CNN. And so here's a quick recap. We've seen that pattern classification tasks, such as does this picture contain a cat, or does this recording contain hello, are best performed by scanning for the target pattern. Scanning an input with a network and combining the outcomes is equivalent to scanning with the individual neurons hierarchically, where the first level neurons scan the input, higher level neurons scan the maps, followed by the lower level neurons, and a final decision unit or layer makes the final decision. And we saw that deformations in the input can be handled by pooling. For two-dimensional and higher scans, this structure is called a time delay convolutional neural network. For 1D scan a long time, it's a time delay neural network. So here's what the convolutional neural network looked like. It comprised convolutional and optional pooling layers, followed by an MLP with one or more layers. And why is this? Give me a second. And here's what the convolutional layer looked like. A convolutional layer had two stages. You worked on all of the maps output by the previous layer. And from those, you first computed an affine map by convolving a filter over all of the maps from the previous layer. So that gave you an affine map. Subsequently, an activation map was computed by applying an activation function pointwise on the affine map. So let's look at how these things work, computing this affine map. Each affine map has associated with it, as we saw, a filter. And so this is what the computation looked like. You have several filters, one for each output affine map. And each of these filters convolves with a set of maps from the previous layer. Again, we also saw that these maps are sometimes called channels. And so each filter, you have as many filters as the number of output maps or output channels you're trying to compute. Each filter has as many channels as the number of input channels, one filter channel per input channel. And so the total number of parameters in any filter is going to be the size of the filter, 3 cross 3 over here, times the number of maps or channels in the previous layer. And so here's how the computation of any given output affine map was performed. Corresponding to each output affine map was one filter. This filter convolved the set of input channels, and we did it like so. You could place the filter on the top left corner of these maps, and then you'd compute an inner product, which is basically a pointwise product of the filter parameter with the underlying map, and then you summed over summed over the entire filter and across all the channels, and you could add a final bias term. So this is how you would compute the affine map term for the top left corner. You got this when you place the filter on the top left corner. And then subsequently, you could stride with the filter and scan the input with the filter. And at each position, you got a corresponding element of the output map. So we saw this in the last class. This is how we computed the convolution. And of course, once you compute this affine map, you next want to apply an activation to it. So the activation function itself applies pointwise. Each ZLIXY represents some xyth element in the ith channel of the Lth layer. To that, you apply some activation function f, and that gives you the corresponding xyth element of the ith channel of the Lth layer activation map. More explicitly, if you wanted to see how the computation was performed, every one of the input channels was used in computing every one of these affine maps. But then each affine map was contributed solely to the computation of the corresponding activation map. So here's your first poll. Can the TS pull up the poll? Okay. Let's see. This poll seems to be the wrong one. Let me end the poll. Sorry, guys. There seems to be some mess up with the polls. So we'll skip the polls. Can somebody just answer this? Is the first statement true? The number of channels in any filter equals the number of input maps, which is the output maps from the previous layer. Is that true or false?
It's true.
True.
First and fourth. You, John, we don't need an attendance poll because Zoom keeps track of everybody who attended. So the first, anybody else is the first. Can you tell me if the first statement is true? Please reply.
It's
Yes.
true. It's true.
Yeah, true.
Just post a yes or no on the chat and we're good, right? I'll be tracking that. Okay. And what about the second statement? The number of channels in any filter equals the number of output maps. Is this true or false?
False.
Number of filters equals the number of input maps. True or false? False. The number of filters equals the number of output channels. True or false? True. Thank you. Right? So you get it. Bear with me, guys. There seems to have been some mess up with the polls. So that sort of went through that was the convolution layers. The other component we saw was the pooling layers. The pooling layers intermittently follow the convolution layers. They don't need to follow every convolution layer. For example, over here, we have two convolution layers and only one pooling layer following it. So here's how we saw the pooling layer operated. You had a pooling filter, which looked at a window of inputs. If you were performing a max pooling, you picked the largest element in this window and copied it out. And then you scan the input with this pooling filter. So if you were performing max pooling, here's how it would be done. You first identify the location of the largest element in the window and then copy that element over. If you were performing mean pooling, then you'd compute the mean of all of the elements in the window, and that's what would go into the output. So you now scan the input using this mean pooling operation. So here's what the computation would look like. Within each window, you compute the mean of that window and then copy that over. So we also saw something else. We saw resampling, which can proportionately increase or decrease the size of the maps by dropping or inserting zeros. In the case of downsampling, we drop S-1 rows or columns between rows and columns. This reduces the size of the maps by a factor S on each side. If you were upsampling, you'd insert S-1 rows or columns of zeros between adjacent entries, and this increases the size of the map by a factor of S on each side. So this is what the downsampling layer looked like. If I wanted to reduce the size of this map by a factor of 2, then all of these black elements in black, these are going to be eliminated. So every second column and every second row is going to be deleted to give you this reduced map. Downsampling literally just drops rows and columns. And the upsampling layer does the reverse. The upsampling layer we saw, if you wanted to upsample by a factor of S, you just insert S minus 1 columns and S minus 1 rows of zeros between any two adjacent element. And this is used explicitly to increase the map size by a uniform factor. We also saw that in practice, downsampling usually follows a convolution or a pooling operation. In this case, you can just think of these operations as convolution with a stride or downsampling with a stride, where the stride is greater than 1. So also in the case of upsampling is generally followed by a convolution, otherwise it makes no sense. And so it's not useful to follow it by a pooling layer, it must be followed by convolution. And this is also often called convolution with a fractional stride. So if I upsample a map, I'd be introducing rows and columns of zeros and then convolving by a filter. And so this is the equivalent term often used is convolution with a stride of 0.5. For reasons that we won't get into over here, this is also sometimes called a transpose convolution. Now, regardless, the point that we are interested in is backpropagation, computing derivatives. And for the purpose of computing derivatives, regardless of the fact that when we actually perform downsampling, that gets merged with the previous operation, whether it be pooling or convolution. And the previous convolution is performed with a stride. We want to disregard this fact. And when we perform backpropagation, we will explicitly separate out the operations of downsampling and the previous operation. So if you had pooling with downsampling, you're going to separate it as pooling with a stride of 1, followed by downsampling. If you had convolution with downsampling, you'd separate it out as an operation of convolution with a stride of 1, followed by downsampling. Similarly, if you're upsampling, instead of having a convolution with a fractional stride or a transpose convolution, conceptually, we will separate it out into an upsampling step followed by convolution. And doing so is going to simplify your backpropagation rules very greatly. We'll get back into this later, but did this point come across? Did you understand what I was saying here? Please say yes or no.
Why we have the one stride in the case of downsampling?
Pardon me?
Why we do have the stride of, why we assume the stride of 1 in the case of downsampling?
So when you're downsampling, here's how you think of it. So when you're downsampling, this is the equivalent of saying I'm overwriting every alternate. If I'm downsampling by a factor of 2, then this is like saying I'm overwriting every second column and every second row with zeros, and then dropping the zeros, right? So we're going to, it's sort of, and that gives us this guy over here. So that means before downsampling happened, you actually had this full map, correct?
Yes.
Or no? Yes.
Yeah.
So we're going to assume that for the purpose of backpropagation, we're going to assume that we actually computed this map and then dropped elements to get this smaller map.
Gotcha.
For the purpose of backpropagation alone.
Thank you.
Okay. And you'll see why when we get to it in the next class. Any other questions? So did this point come across, guys? I'll wait for a yes or a no, because I don't see any responses on chat. So, okay. I see a bunch of yeses. All right, great. So let's continue. Now, so we also saw that when we had an end-to-end CNN, for a typical image classification task, you'd have a bunch of, you'd have an image would have several channels, in this case, the color channels. You'd stack them up. Wait. You'd stack them up and then process them with a sequence of convolution and pooling layers. The output of the final layer is going to be flattened And that flattened output is going to be put through an MLP to get your final classification output or regression output if that's what you're performing. So this is how we set up a typical CNN. The parameters over here are going to be the filters that operate on the various convolution layers and also the parameters of the final MLP. And these are the ones that must be learned. These are the ones that must be estimated. So again, as a quick recap, training, we saw that a CNN is basically scanning with an MLP with shared parameters. So training is just as in the case of the regular MLP. The only difference is in the structure of the network. You're going to be providing examples of the image and the class, which define a loss, which is a divergence between the desired output and the true output of the network in response to any input. And the loss, of course, aggregates the divergence on the training set. The network parameters are trained to minimize this loss through variance of gradient descent. And gradients are computed through backpropagation. So here again, for any individual instance, you pass the instance through the network. There would be an output. There's going to be a desired output for that input. You can compute a divergence between the two. And so this is the divergence or the loss for a single instance. The overall loss is going to be the average of this divergence for the entire training set. So again, you'd be given a training set of input-output pairs, which might be images and class labels. And so if the divergence on an individual instance is represented as div, yi, di, yi is the output of the network, di is the desired output, then the loss is the average of these divergences over the entire training set. And we want to minimize this loss with respect to the parameters of the network, all the filters and the MLP parameters and biases. So again, the loss is the average divergence over the entire training set. So when you compute the derivative of the loss with respect to any parameter is also the average of the derivatives of the divergences for the individual instances with respect to the parameter. And so this is the term that we would have to compute all over again, just like in the case of the MLP. So how would we go about it? For any individual instance, you're going to get an output of the network. You can compute a divergence between this output and the desired output. And then you can backpropagate the derivatives of the divergence to the first layer of the MLP. And then from here on, so until here, you'll just be doing the conventional backpropagation for the MLP. Now, here's where things get a little interesting. So let me see if I can get my pointer out. Bear with me, this is. So remember that at the final layer, here's what we did. We took our maps and then we unrolled this into a vector. So if we had several maps, all of these would be unrolled jointly into a large vector. And this is what you'd be computing your MLP over. So when you compute your derivatives backwards, you'd get the derivatives for all of these elements. These derivatives can now be folded back into the shape that they were unrolled from in the first place. And so now you're going to have the derivatives of the divergence with respect to the elements of the maps in the final layer of the convolutional component of the network. Did that make sense? That makes sense, guys? Okay, good. So that's where we're going to have to go back from. Now, let me get back my pointer options. Okay. So now we must perform backpropagation from here backwards through the convolutional layers. And this requires special consideration of the shared computation on the convolution layers and what happens in the pooling layers. That's what we're going to look at. So I'm going to assume that from the divergence for any individual instance, we are going to get the derivatives for the maps, for the final output maps. And from there, remembering the forward computation, during the forward computation, the previous layer maps were operated on by channels to get an affine set of affine maps from which the activation maps were computed. So when you go back, initially you'd have the derivatives for for every element, for every one of these output activation maps. And we must go backwards from there and first compute the derivatives for the affine maps. And then from those, you must continue backwards and compute the derivatives for the elements in the previous layer maps, and also the derivatives for the filters. So this is what we're going to have to do. And so for the convolution layers, we're going to have to figure out how to compute the derivatives with respect to the affine combination Z from the activation output maps Y, and then how to compute the derivative with respect to YL minus 1, which is the previous layer, and the Lth layer filters, given the derivative for the affine maps of the Lth layer. Then for the pooling layer, you had some pooling operations which operated, on individual maps to get the corresponding pooled maps. So now, assuming that we have the derivatives with respect to the output of the pooling, we have to figure out how to compute the derivatives for the input of the pooling. So for pooling layers, the challenge is how to compute the derivative with respect to Y of L minus 1, given the derivatives with respect to YL, which was computed by performing a pooling operation on YL minus 1. So these are the challenges we must resolve. So let's first look at convolution layers. Any questions so far? Did you get what we are speaking of so far? Questions? No questions. Okay. So let's see this. First, how do I compute the derivatives with respect to the affine value terms from the output activation map? So here, again, we assume that we worked our way backward and have the derivatives with respect to all the y's. But the y's were obtained by applying an activation function pointwise on the z's. So for the mth channel of the Lth layer, the y value at position xy was obtained by applying an activation f on the xy element of the mth affine map of the Lth layer. So assuming now that I have assuming that I already have this term, the derivative of this is writing with respect to y, I'll drop the L and N. Assuming I have this. Why is this not writing? I'm trying to write, okay. Try right here. So from this, how can I compute the derivative with respect to the z? Anybody? How would I get this? Anyone?
It would be the derivative of the activation function because Z is.
So I can just say d div over dz xy is simply going to be d div over dy xy times the derivative of the activation function, correct? Element wise. So we are not yet speaking of max pooling. This is the activation function which applies on the z's to get your y's, okay? So that's what we're going to do. The derivative of the divergence with respect to z xy is the derivative of the divergence with respect to y xy times the derivative of the activation function computed at zxy. So that clear so far? Questions? Is this clear? No. Okay. This was the easy bit. Okay. So I'm going to assume now that this is figured out. We know how to compute the derivative with respect to the affine term z from the derivative for the activation values y. So now we have to figure out how to compute the derivative for the previous layer maps and the filters given the derivatives for the affine terms. So again, during the forward computation, we computed these affine values from the previous layer maps and the filters. So during back propagation, given the derivative with respect to z, we must compute the derivative with respect to y and the derivative with respect to the filters w. Let's see how we can do this, right? First, let's see how we can compute the derivative for the previous layer maps. So here again is where we are. We have managed to back propagate and compute the derivatives of the divergence with respect to every element of every one of these affine maps. And so now we want to propagate the derivative backward and compute the derivatives of the divergence with respect to every element of every one of these previous layer maps or channels. Let's see how we can do this. Now remember that every channel of the previous layer was used because the filter has as many channels as the input channels, right? So every channel of the previous layer was used in the computation of any given affine map. And so if I just want to shorten this, simplify the picture, the first channel of the L-1th layer convolved with the first channel of the nth map, the second, and so in general, the mth channel of the L-1th layer convolved with the mth channel of the nth map to give you the nth channel of the affine map in the forward pass. So if you draw all of the dependencies, every one of these input channels was used in the computation of every one of these output channels, and every one of these output channels in turn was used in the computation of the divergence. So if I want to compute the derivative of the divergence with respect to any specific input channel, I have to track the dependencies from this input channel to the divergence. And so if I chose this input channel, that's what the dependencies are going to look like. So what does this mean? If I want to compute the derivative of the divergence with respect to this guy, how does the fact that this one influences all of the output affine maps affect our derivative? Anybody? How would it affect it? Anyone? So, does nobody want to respond? Let me see if I can. Let's consider. So what this means is that I'm going to have the figure answers right here. You're going to have to compute the derivative of the divergence with respect to this map. You're going to have to sum over all of these guys. And so the actual derivative of the divergence with respect to this term is going to be the sum over all of the affine maps of the product of the derivative of the divergence with respect to the affine map elements times the derivative of the affine maps elements with respect to the y's. So that's what this equation here says. And during the backward pass, we already have the derivatives of the divergence with respect to the affine map elements. So the term that remains to be computed is the second term, which is the derivative of these affine map elements with respect to y. That makes sense? Did that make sense, guys? Okay. So now this is the term we need to figure out how to compute. And to do that, let me focus on just one output affine map. How does this y affect this particular z? Okay. So to do that, we'll do that using a picture again. Now, consider this element of y. And let's see, and so this is the output affine map. The filter is shown in orange. Now, clearly, this element of this input channel is being used in the computation of this first output element, right? But then as the filter goes forward, you can keep track of which are all the output elements that this particular element is being used to compute. And we find that this element was used in the computation of 4 of the output elements. And in fact, in general, we can just assume that any input element over here is, going to be, in the worst case, involved in the computation of every one of the output elements, right? And not just of this one channel, because the filter itself has many channels. It means that because this input channel is being used to compute every one of the output channels, it means that this element was used effectively in the computation of a whole bunch of elements in every one out of the output affine maps. And so, if I want to compute the derivative of the divergence with respect to this xy element of the input channel, I'm going to have to sum over all of the output affine maps. And within each of the affine maps, I'm going to have to sum over all of the elements. And at each element, I'm going to compute the product of the derivative of the divergence with respect to that element at x prime, y prime, times the derivative of that element with respect to this guy. So did this equation make sense? Yes or no?
No.
Yeah.
No.
Okay. And of this, we already know this first term. We are assuming that during backpropagation, this has been computed. So the only term that remains to be computed is this second term. And what is this second term? If I work it out, let's look at this pictorially, right? So here is an input channel. Here is a filter corresponding to this channel. And I've represented the elements of the filter using 2 different codes. One is a color code, the other is a numeric code. So the color code shows you the position, so does the numeric code. The numeric code also shows the position. I'm assuming indexing begins at 0. So when I place the filter at the 0, 0 element, I'm computing the 0, 0 element of Z, right? But in so doing, Y22 is multiplying the red element of the filter, which is the 2, 2 element of the filter. So Z00 has a contribution from Y22 times W22. If I slide the filter forward 1, now Z10 is obtained in part by multiplying Y22 by W12, as you can see from the color, right? Z20 has a contribution from the product of Y22 and what are we multiplying Y22 by in this case? Anybody?
0, 2.
0, 2,
0, 2
right?
in the filter.
And so you can see how this works out. At each point, the Y22 is multiplying a different element of the filter to contribute to a different element of Z. So what does its relationship look like? If you go through all of these relationships, all of these equations that I showed over here, you're going to find in general that to compute the Z value at any x prime, y prime, Y22 is multiplying W of 2 minus x prime, 2 minus y prime. So you can verify this, right? So over here at let's look at Z0, Y22. When this is 0, 0, this is 2, 2. When this is 1, 0, this is 1, 2. So the indices of the Z and the W add to give you the index of the W, of the Y in every case. Can you see that? Can you all see this, right? So and there's nothing special about Y22. So I can write a general equation. I can say Zx prime y prime for any yx5. I'm going to get, Zx prime y prime is yx pi times W of x minus x prime, y minus y prime. In other words, the index of the Z and the index of the W will sum to give you the index of the Y. So this means that the derivative of zx prime y prime with respect to yxy is simply going to be the filter value at x minus x prime, y minus y prime. This making sense? Right. What about the rest of you guys? Okay, and so I can just plug this here, right, into my equation here. This guy, I can just replace that by x minus x prime, y minus y prime. And so this is how I would compute the derivative for every element of every input channel. Now this, so here's the second pole. I don't know if we'll get up the poles. So, yeah. There was supposed to be 2 questions. There's some kind of a mix-up, nonetheless. So let me just try to stop this poll. And can you just tell me collectively what the first answer to the first question is? So what about the second question? Also true? Okay. Guys, we'll fix the poll next week. We're having an issue this week, right? So in order to compute the derivative at a single affine element, we must compute the contributions of every position of every affine map at the next layer. So the derivative of a single affine element will require summing over every position of every Z map in the next layer, right? Both of these are true. So here is what the derivative looks like. But then this, it turns out, is actually a convolution. How is it a convolution? Let's see. So let's go back to this picture, right? So y22 multiplied the red element of the filter to compute Z00. So for 22 alone, I am painting the 00 element of the output with the filter element that was used to compute it. Okay. So is this notation clear? For just the 22 element, I'm painting the 00 element with the red to show that it was the red filter element that was used to compute it. Is this making sense to you? Okay. What about the rest of you guys? Okay. And so when I go forward, y22 multiplied this element of the filter. So for the 10 element, the pink element of the filter was applied, and so on. And so as you go forward, what you find is that here, when I'm computing y22, when I'm computing the contribution of y22 to every one of these Z elements, here is the pattern of weights that was applied. So now if I were to compute the derivative of the divergence with respect to y22, it means that I'm going to have to multiply the derivative for Z00 by the red filter element, the derivative of Z at Z10 by the pink filter element, the derivative at Z20 by the green filter element, and so on. So did this make sense? Right. What does this look like? Now, what is this pattern of colors? How does this pattern of colors relate to the pattern of colors over here? It's flipped. It's flipped left, right, top, bottom. It's transposed, right? Moreover, so this looks like I just flipped the filter both ways. And where did I position the filter? I positioned the filter with the 00 element of the filter at 22. Did you see that? And so, in general, here's what we're going to find. If I want to compute the derivative of the divergence with respect to y22, I'm going to have to flip this filter and place it on the derivative map for Z with the top leading corner now sitting at 22, and then just perform an inner product. Or more generally, for any xy, to compute the derivative for yxy, I'm going to have to flip the filter and place it with the bottom right corner at X bar and compute the inner product. Does this make sense? Okay, and so, but that's just one channel, right? One output. So here's what it looks like. Here is the filter, right? Let's say I have the derivative of the divergence with respect to all the z elements. I want to compute the derivative of the divergence with respect to all the elements of Y. Now here's a general principle, which I'm going to try to write if I can get my pointer options working. So let's say if I have any number of elements k cross n going into some operation, and the output is some, say, L cross n, right? And then this is used to compute the derivative of the divergence. It doesn't matter what these guys are. When I compute the derivative going backwards, every one of these elements was eventually used in computing the divergence, right? Yes or no? Which means, what is the size of the derivative I must get over here? It must also have k times n elements, correct? Exactly, because every one of them was used in computing the divergence. So what this means here is that although let me get my pointer options back. Although the z map is smaller than the y map, when I compute the derivative going backward, the derivative must have the same size as the original y map. Does that make sense? Okay. Now, why did the y map become small over here? It became small because this filter could not fall off the edge, right? So we could only slide it forward so many times. So if the filter is k wide and k tall, what we are going to do is zero pad the derivative map for z with k rows and k columns of zeros and k minus 1 rows and columns of zeros on every side. And then subsequently, we're going to flip this filter left to right, top to bottom. And then you place, so all of this blank area are zeros. And now I can place my flipped filter starting at the 0, 0 position to get you the derivative and perform an inner product to compute the derivative at the 0, 0 position over here. And so I can keep sliding forward and computing the inner product. And what does this look like? What is this operation, guys? What is this operation? Anybody?
Convolution.
Right? Except that we are convolving the flipped filter with the zero padded derivative map for the z. Does that make sense? And now, when you flip the filter, so here's something else that happens. Let's see that the sizes line up properly first. If this guy was, say, n cross n, then and if this was k cross k, then the z is going to be n minus k plus 1 times n minus k plus 1, right? So, but then when I pad it with k minus 1 zeros on both sides, it becomes plus 2 times k minus 1. So this becomes n plus k minus 1 after padding, right? Yes or no? But then when I convolve this n plus k minus 1 with a k cross k filter, I'm going to lose k minus 1 elements, k minus 1 rows and k minus 1 columns. Because convolution loses the boundaries. And that's going to give me a resulting n cross n derivative. Does that make sense? Okay. What about the rest of you guys? Did that make sense? Any questions? And so, but then again, remember that each element was involved in the computation of all of the filters, right? What I showed you was the contribution of just one of these filters to this derivative. So to compute the overall derivative of the divergence with respect to any map, here's what you're going to do. You're going to pull out the corresponding channel of all of the filters. So these are the, so if I'm computing the derivative for the mth input map, here are the mth channels for all of the filters. And here are the corresponding derivative maps for all of the output channels, all of the, right? You're going to zero pad these guys. And each of these filter channels is going to be transposed, flip left to right, top to bottom. And then this one is going to be convolving the flipped filter, which is now going to have as the flipped entry over here is going to have as many channels as the number of output maps. And that's because we chose the nth channel, right? So I have n output maps. I have a certain number of output maps. That's going to be the number of filters, but I'm pulling the nth channel for all of these guys. So this is going to have as many channels as the number of output channels. And so when I transpose it, this is going to be the same size as the number of output channels. And so I can just convolve it. And that's what is going to give me the convolution for that's what is going to give me the derivative for the input channel. Did this make sense? So, Kishore, I'm not sure I understood. This is exact, right? There's no sharing. For any given input channel, I pull out the corresponding channels for all the filters, transpose them, and then I zero pad the output channels or the derivative maps for the output channels and convolve them with a transpose filter. That's it. So,
Doctor.
any questions? Kishore, did that answer your question?
I have one clarification, Doctor.
Yeah.
So this is for one input map. Yeah. What if we have 4 input maps? Then,
So for input, pardon me, this is for one input.
yeah, this is for one input channel, right? What if we have 4 input channels?
So you'll be doing this separately for each of the four input channels. For the first channel, you'll be pulling out to compute the derivative of the, let me go back here. These animations are painful. Good. So to compute the derivative for the first input channel, you'll be pulling these guys out. To compute the derivatives for the second channel, you'll be pulling these guys out, and so on. Of course, the whole thing can be bashed into nice vector operations, which is what your PyTorch does, but this is the basic operation.
Okay, thank you, Doctor.
Right? So this is what we do. Any questions? I'm assuming not. Okay. And so this is, if you do this, the size of the there's some text over here, you can bypass those, but basically what this is saying is that the size of the derivatives that you get is going to be the same as the number of elements in the original input map. And if the original input map was zero padded in the forward pass, the derivative map that you get back is also going to have derivatives for all of the regions that were originally zeros. So these things will have to be thrown away. Okay, because they're just zero pads. Now, hopefully this poll works. Okay, 10 seconds, guys. Okay, this again. We've had some issues with entering the polls this time, so I'll just end the poll, but we have to figure out what's going wrong with the polls. Zoom polls are a bit of a mystery. But anyways, so just to go over this. The Zoom needs debugged. Basically, can you tell me which of these elements are true? Just reading this. Which of these? Anyone? To compute the derivative with respect to the mth activation map of the nth convolutional channel, we must select the mth channels, right? They must be flipped up and down. They must convolve the derivative maps of the L plus 1 affine maps. The output doesn't need to be flipped again. Thank you, right? Again, my apologies for the messed up poem, okay? So we now have the derivatives for all of the y's. And this can be computed by convolution with a flipped filter. I have some pseudocode for it. It's fairly straightforward. You can just use the same convolution code you have going forward to compute it. So this gives us the derivative for the y's. The next is the derivative for the filter weights, right? How does that work? Now, this is when I place the filter, in order to compute the output at any location, every filter element is used, but then every filter element is used in the computation of every output location, right? So this is supposed to have some. This is really a horrible animation thanks to whatever core software I used to generate it. But the point is, you can see that every single filter element is used in the computation of every output element, right? So this means that to compute the derivative of the divergence with respect to any filter element, I must sum over all of the output elements. Exactly what will I sum? Now look at it this way. Say when if I am operating on the previous layer to compute a single affine map, then the filter is going to be placed on the previous layer channels. But any given channel of the filter is going to operate only on the corresponding input channel. And it's going to generate just a single output map. So the thing about the filters is that each filter channel operates on a single input channel and generates a single output channel. Nevertheless, when I actually compute the derivative, so this is the forward equation, right? So if I look at, say, a single filter element like this guy, you can see that that filter element only influences a single output channel and only operates on a single input channel, right? Moreover, now look at the equations on the right-hand side. So if you look at the equations on the right-hand side, let's look at how filter element 1, 2 is used in computing the different z elements. Filter element 1, 2 multiplies y element 1, 2 to compute z element 0, 0. Filter element 1, 2 multiplies y element 2, 2 to compute z element 1, 0. 1, 2 multiplies 3, 2 to compute z element 2, 0, and so on. Is this relationship seeming familiar? We saw this earlier, right? Anybody remember? What did we see just a few minutes ago? The indices of z and w must sum to give you the index of y. Remember? Right. And so if I actually go through this sequence of computations, here's what you're going to see. Zxy, right? To compute Zxy, Wx prime y prime must multiply y x plus x prime. This should be y plus y prime, right? because the indices of Z and W must sum to give you the index of Y. That makes sense? Yes, no? Okay. So in general, ZXY is going to have, there's a plus equal to, right? Which the, why is this thing not showing up? Zoom is much slower than, yeah. So in general, you're going to get ZXY is, oh gosh. What I'm seeing on my screen is much slow, very different from what's showing up on Zoom. Okay, so ZXY, to compute ZXY, this should be a plus equal to, you multiply Wij by Y x plus I, Y plus J. Oh, come on. Sorry, guys. This lag is killing me, right? So ZXY multiplies Wij to get ZXY. The contribution of Wij multiplies Y of x plus I, Y plus T, right? And so if I want to compute the derivative of Z with respect to any ZXY with respect to any Wij, that's simply going to be Y x plus I, Y plus T. Right? So this making sense? There's a bit of a lag between my voice and this is what's on the screen because there seems to be a transmission delay, but is this making sense? Right. And so if you look at this equation at the bottom, the derivative of the divergence with respect to Wij must sum over all the elements of the output map. And the term that summed is the product of the derivative of the divergence with respect to ZXY times the derivative of ZXY with respect to Wij. And the derivative of ZXY with respect to Wij is simply this guy here. This is already computed. And this term is simply going to be Y x plus I, Y plus J. And so I can plug it in here. And that's going to give me my derivative equation for the filter. So this making sense so far? Okay. But does this equation look familiar? What does it look like? What does this look like, guys? So it's a convolution, right? So I'm going to skip the next 2 slides simply because the lag is killing me. But you'll have to sort of believe me on this. Here's what actually happens. This is, this is the equation we have. The derivative of the divergence with respect to any ij element, Wij, sums over all the elements of the derivative map for the output channel. And the term that summed is the product of the derivative of the divergence with respect to the xy element of the output map times Y x plus I, Y plus J. And this is a convolution of this kind, right? Here's what it looks like. If I can say, let's say these are all the input channels. These are all the output channels, 1 channel per filter, right? Then any single channel of the filter connects the corresponding input channel to the output. And so to compute the derivative of the divergence with respect to this filter channel, you consider the derivative of the divergence with respect to all the elements of the output map. And here's how you would do it. You literally just convolve the derivative map for the output channel with the original input channel. And this convolution will give you the derivatives of the divergence with respect to that corresponding channel of the filter. That makes sense? Right. And so can you check, can you verify that the sizes are now correct? Because the size of the filter output channel plus the size of the filter minus 1 is going to be the size of the input channel, right? So also the size of the input channel minus 1 less than the size of the output is going to be the size of the filter. And so the sizes match. So if I want to compute the derivative for all the channels of a filter, I just have to convolve all of the input channels with the corresponding derivative map for the output channel. And that's going to give me the derivatives for, that's going to give me the derivative for the entire filter. Does that make sense? So there's just a single yes. What about the rest of you guys? It's easy computation, nothing fancy, right? So although the math looks very ugly, it's actually very easy. And of course, you have to keep track of all of the stuff like zero padding. If the input channels were zero padded in the forward pass, it must be zero padded for backprop. But this is really just the equation for computing the derivative for filter elements. So I'm not going to go through the Zoom poll unless this works. Let's see. This is messed up. Skip the Zoom polls, right? No, this poll doesn't work. The text is bunkum. So I'm going to skip this. Okay. All right. So is the first statement true? The derivative of the nth channel of the nth filter is computed by convolving the nth input channel with the nth output layer derivative map. And does it need any flipping? No, right? So the first is true and the second is false. So I have the pseudocode for it. So we've seen the derivatives for both the filter and the input channels, right? It turns out that if you look at it through the lens of code, it actually looks much simpler. And for this, we can do through the application of two simple rules. If I have y equals sigma of z, then dl over dz is dl over dy times sigma prime, right? Also, if I have z equals wy, then dl over dy equals dl over dz times w plus equals, right? Because y may have y may be contributing through other means to L also. So also dl over dw plus equals y times dl over dz. So this is just a very simple rule for computing derivatives. And so when you do the CNN forward pass, here's what the CNN forward pass look like. You are scanning, and at each position, when you computed the affine term, you were multiplying the weight and the y, right? So this is the output channel, the input channel, and the weight that multiplies it. And then finally, when you got the affine term that was put through the affine term z that was put through an activation to get y. So because it's backprop, everything is going to be inverted. Instead of going from 1 to the end for the loops, 1b for the loops, and then having y at the bottom, we're just going to flip everything top to bottom, left to right. And so this is what the code will look like. This first y equals activation z is going to become dz equals dy times the derivative of the activation. And then we're going to use the other rule, right, which is this guy. If I have z equals wy, then the derivative of the loss with respect to y is the derivative of the loss with respect to z times w. And the derivative of the loss with respect to w is the derivative of the loss with respect to z times y. So that's what we do here. All I did was I said, again, observe that z equals w times y. Note the indices. I'm going to use the self-same indices and say the derivative for y is going to be the derivative of z times w, and the derivative for w equals the derivative for z times y. I just literally just took the code and flipped it, flipped all the loop indices in their order. And within the loops, I computed the derivative of the last operation. And within the affine computation, I just, where he had z equals w times y, I said the derivative for y equals w times the derivative for z. And the derivatives for w equals y times the derivative for z. So just a simple flip of the code. And this is a lot simpler than in terms of understanding than the convolution. It would, but just pointing out that even when you're performing convolution, this is basically what you're doing. That's all. Okay, now let me try to move on. And this whole thing can be cast as a tensor or vector operations. We're not going to discuss this. For some reason, there's a terrible lag between my screen and your screen, and so this is really killing this class. But here, we've figured out how to compute the derivatives for affine maps as well as the from the output maps, and also how to compute the derivatives for the previous layers and the filters, given the derivatives for the affine terms. So I think what she's speaking of is in terms of computation. It's going to really be very slow if you have those many for loops. But then if you were using some kind of tensor operations and GPUs, you wouldn't actually be writing for loops. Anyway, so for our purposes, we have figured out, please move, how to compute derivatives for convolutional layers. The next is how to compute derivatives for the pooling layers. So let's see how we can do this in the remaining 12 minutes. Again, remember that when we were performing pooling in the forward pass, if you were performing max pooling, as you scanned forward at each entry, you were simply picking up the maximum element of the window and copying it over. So now tell me this, if within this group, if I perturb this element 1, would this change the output? Which is the only element in the input that I could perturb to change the output, right? So this means that for the first 3, so the max operation is going to basically follow the same sequence of operations as it scans. And I'm assuming that the stride is 1. But when you're performing backprop, here's the rule that happens. The derivative going backwards, you're going to get the derivative with respect to this element 6. Now, that derivative is going to be copied directly over to the position where the 6 came from. And since the other 3 did not affect the outcome, their derivatives are going to be 0. Does this make sense? What about the rest of you guys? Right. And so if I were to look at it in terms of code, here's what this is going to look like. Remember, when you were going forward, you actually stored the index of the maximum location at each position on the during pooling. So when you're going backwards, all you will do is increment the derivative at that position, the derivative for the upward. Now, why am I using it over here? Anyone?
Oh, the
Why
audio.
am I using a plus equals? So here's what would happen. The derivative of a constant number. So Birhanu, I'm not sure I understood that. We know that the previous layer y element at this location was copied to the output, right? So the derivative the derivative at this element must just obtain the derivative from the output going back, and the rest of them obtain no derivative. But then what happens is that when you're scanning forward, the same element may be the maximum element in more than one window over here. And so if this element, for example, is the maximum in 2 consecutive windows, then it's when you're going back, you're going to get contributions from both of those locations to the derivative over there. Does that make sense? Yes, no, guys. So again, my apologies for the very crappy internet connection. I didn't expect this, so things are slow. Okay. What about mean pooling? In mean pooling, you're taking the average of the elements in a window and copying it over, right? So what this means is that if this window has 4 elements, this derivative is going to be 1/4. This element is going to be 1/4 the element here plus 1/4 the element here plus 1/4 the element here plus 1/4 the element here. So when you're going backwards, the derivative that you got at the output, which is this term here, is going to have to be uniformly shared across all the elements of the input window, because each of them contributed 1/4 in this case to the computation of the output. Did that make sense? Right. So why would the elements have different weights? Remember, when you're going forward, you just took the average of these guys. So this is going to be 1/4 plus 3/4 plus 6/4 plus 5/4 to give you 3.75. So when you're going backwards, this derivative times 1/4 comes here. This derivative times 1/4 comes here. This times 1/4 comes here. And this times 1/4 comes here. Did that clear that particular doubt? Right. So if I were to write the pseudocode, this is what it's going to be, right? In the forward pass, we just computed the mean of each window. So in the backward pass, you're going to just increment the derivative at each location by 1/4 or 1/k squared, where k is the size of the pooling window, right? Of the derivative at the output of the pooling. And you're just going to, again, this increment because the same element may be used in adjacent windows. This makes sense? Okay. And so we have shown the derivative of the divergence with respect to every intermediate output and every free parameter. This can be embedded in gradient descent to learn the network. And we're still missing one element, namely resampling. So I'll cover resampling in the next class. And so here is the story so far. The convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, followed by an activation, and pooling layers that operate over groups of outputs from the convolution layer and typically include downsampling to reduce network size. You have optional resizing operations, typically performed through strides greater than 1 for downsampling or interpolation of zeros for upsampling. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element in each pool. Other pooling operators can use regular gradients as subgradients. And derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. And what we saw were some of the rules for sharing, but all of this makes the computation of derivatives look just like a convolution operator. So we'll stop right here. This slide should have really been online. I'm not sure why this was not, but we'll make sure that the slides are out from the next class. My apologies for today. I did not check, or I'd have made sure that the slides were online. So, any questions? So if we have no questions, with apologies for the very messy transmission, I'm going to stop my slide share and terminate Zoom. Thank you all. So I don't think it's just a question of the camera. I think I'm here at the Mohammed bin Zayed University of AI, and